Welcome to SciSense, where we unwrap scientific research, because science should not be a puzzle.
Welcome to the SciSense podcast. I am Sarah, and I am here with Mike. Today we are going to talk about quantum computers, and we are going to make this really accessible because there is a paper just published in the journal Physical Review X by Fabrizio Berita and colleagues at the University of Copenhagen that has made a breakthrough in one of the biggest problems holding quantum computers back.
Okay, I have to be honest. Quantum computing is one of those topics that always sounds incredible, but I never fully understand. Can we start from the very beginning? What actually is a quantum computer?
Absolutely. So a regular computer, the one in your phone or on your desk, stores information as bits. Each bit is either a 0 or a 1. Think of it like a light switch. It is either off or on. A quantum computer uses something called a qubit instead. And a qubit is special because it can be 0, 1, or, and this is the weird part, a mixture of both at the same time. This is called superposition.
A mixture of both? Like the switch is half flipped?
Kind of, yes. Imagine a coin spinning in the air. While it is spinning, it is not heads or tails. It is both, in a sense. Only when you catch it, when you measure it, does it become definitely one or the other. A qubit is like that spinning coin. And because qubits can explore many possibilities simultaneously, quantum computers can solve certain problems astronomically faster than regular computers. We are talking about problems in drug discovery, materials science, cryptography, things that would take a regular computer millions of years.
That sounds amazing. So what is the problem? Why do we not already have these working everywhere?
Noise. That is the single biggest obstacle. A qubit is unbelievably sensitive to its surroundings. The tiniest disturbance can destroy the quantum information it is holding. A stray magnetic field from a wire nearby, a tiny vibration, even a cosmic ray, a particle from outer space, hitting the chip. Any of these can knock the qubit out of its delicate quantum state.
So it is like trying to balance a marble on top of a basketball. Any tiny nudge and it falls off?
That is a brilliant analogy. Exactly like that. And the way scientists measure this fragility is with something called the T1 time. T1 tells you how long a qubit can hold on to its information before the noise destroys it. Think of it like a timer. The moment you store information in a qubit, the T1 clock starts ticking. When it runs out, the information is gone.
So you have to finish your computation before the clock runs out.
Exactly. And here's the real problem that this paper addresses. Everyone assumed the T1 time was fairly stable. Maybe it drifts slowly over minutes or hours. But it turns out T1 fluctuates wildly, and it does so extremely quickly. One moment your qubit might hold information for 100 microseconds. A fraction of a second later, it might only last 10 microseconds. Imagine you are running a race, but the finish line keeps moving closer and further away unpredictably. That is what the qubit is dealing with.
That sounds like a nightmare for trying to do reliable computations. So how were people measuring these fluctuations before?
The fastest methods before this paper could track T1 changes on the timescale of about a millisecond. A millisecond sounds fast to us. It is 1,000th of a second. But in the quantum world, that is actually really slow. It is like checking the weather once a day when actually there are thunderstorms rolling through every few minutes. You would completely miss them.
So you would think the weather is calm when actually it is chaos.
Exactly, and that is precisely what was happening. Now, what this Copenhagen team did is truly ingenious. They built a system using something called an FPGA. FPGA stands for Field Programmable Gate Array. Think of it as a custom-built computer chip that can make decisions incredibly fast in billionths of a second.
Like a purpose-built brain for this one specific task.
Perfect way to think about it. And they programmed this chip to run something called a Bayesian estimator. Let me explain what that means with an analogy.
Please do.
Imagine you move to a new city and you are trying to figure out what the weather is like. You have no weather app, no forecast. But every minute, someone walks past your window. If they are carrying an umbrella, that is a clue it might be rainy. If they are wearing sunglasses, that is a clue it might be sunny. Each person gives you a little more information, and you keep updating your best guess about the weather.
So you build up a picture over time by combining lots of small clues.
Exactly, that is Bayesian estimation. And this chip does the same thing with the qubit. It pokes the qubit, measures whether the information survived or decayed, and uses that as a clue about the current T1 time. Then it does it again and again. Thousands of times per second.
Thousands of times per second.
Yes. Each measurement updates its estimate in about 1 microsecond. That is 1/1,000,000th of a second. So it is building an incredibly detailed, real-time picture of how noisy the qubit's environment is at any given moment.
And what did they actually discover when they turned this on?
This is the jaw-dropping part. They found that the noise inside a quantum computer is 10,000 times more turbulent than anyone had detected before. There are fluctuations happening on timescales of just 10 microseconds. The quantum world is not a calm pond with the occasional ripple. It is a raging sea with waves crashing constantly. And we simply could not see it before because our tools were too slow.
That is extraordinary. But what is actually causing all this noise?
One major culprit is something called two-level systems, or TLS, S for short. These are tiny atomic-scale defects in the materials the qubit is made from. Imagine there is a microscopic light switch embedded in the material, and it randomly flips between on and off. Every time it flips, it changes the electrical environment around the qubit, which changes how noisy things are. With this new tracker, the researchers could actually watch individual defects switching on and off in real time. Nobody has ever seen that before.
Like catching the troublemakers red-handed.
Exactly, and that is incredibly valuable because once you can see the individual sources of noise, you can start figuring out how to engineer better materials to eliminate them. But here is what really excites me about the practical impact of this work.
Tell me, what does this actually mean for the future of quantum computing?
It is potentially game-changing, and here is why. Current methods for protecting quantum computers from errors, what we call quantum error correction, are built on the assumption that the noise is relatively steady. They are designed for calm weather.
But if the noise is actually changing thousands of times per second like they found.
Exactly, then those protection methods are not nearly good enough. This research tells us we need smarter adaptive error correction.
Adaptive meaning it adjusts in real time.
Exactly. And the beautiful thing is, the researchers already demonstrated this works. With their real-time noise tracker, you can see when the qubit is having a calm moment and when it is in a storm. So you run your quantum operations during the calm windows and hold off during the noisy ones. Think of it like a pilot rerouting a plane around a thunderstorm instead of flying straight through it.
And they showed this actually improves results?
Yes. They showed that this adaptive approach improves computation quality without changing any of the hardware. No new chip, no new refrigerator, no new materials. Just better information about what is happening in real time.
And this scales up to bigger quantum computers too?
Absolutely. As we scale up to quantum computers with thousands or even millions of qubits, having this kind of real-time monitoring on every single qubit will be absolutely essential. It is like installing a weather radar system inside every quantum computer.
So to sum it up, they basically gave quantum computers the ability to see their own noise for the first time.
That is a perfect summary, Mike. And in quantum computing, seeing the problem clearly is more than half the battle. This could be one of those papers that people look back on as a turning point.
Incredible stuff. Thank you for making that so clear, Sarah. I actually feel like I understand quantum computing a little better now.
That is the best thing I could hear, Mike. The quantum future just got a lot less noisy.
Thanks for listening to SciSense. Share it with a friend. See you next time.